Hello everyone, my name is Vaibhav Venugopal. I'm a PhD student at Drexel University. Today my presentation is about the security vulnerabilities of the 2.5D and 3D integrated circuits. So this is the overview of the presentation. So we'll be introducing the need for the vertical integration, security advantages and challenges of the vertical integration, hardware Trojans and security side security side channel attacks on the 2.5D and 3D integrated circuits. Technology scaling has been impetus for the advancement of smaller, faster, more efficient ICs with increased functionality. Even though the technology scaling has resulted in reduced per transistor cost, the hidden cost of R&D and setting up a new fabrication facility is very high. In addition to that, the wafer cost has steadily increased as the technology has advanced. The use of the advanced technology node also has led to the increase in the IC failure rate and as well as increase in the design complexity and resources. Vertical integration is a form of technology that is orthogonal to that of the technology scaling. Some of the benefits of vertical integration are increased performance due to the heterogeneous integration of analog digital memory and sensors in a compact and reduced space. In addition to that, vertical integration leads to reduced interconnect lengths, thereby reducing the delay and increasing the bandwidth. The vertical integrated circuits are fabricated in a less advanced technology node. Therefore, it is cheaper to fabricate, and as well as it has increased the reliability and lifetime for the use of the IC. Coming to the form factor, the vertical integrated circuit increases the number of transistors, increase functionality, and reduce the IC dimension. So here, instead of fabricating in a die area of 14 millimeters squared, the same die is split into two dies of 7 millimeters squared. Therefore, this has reduced the area without affecting the functionality of the circuit. One example of the vertical integrated circuit is the 2.5D IC, where different dies are fabricated in a different technology node, and they are chip bonded into an interposer. The interposer works as a interconnect medium and form of a communication between the dies. Another example of the vertical integrated circuit is the 3D IC. So in the 3D IC, each die are fabricated in a same or different technology and at different foundries, and they are stacked on top of one another. And the communication medium between all the dies is through silicon vias or TSVs. The TSV is a high performance interconnect, and this is fabricated as a through die or a through wafer. The main advantage of the vertical integrated circuit is that it enables the IC to be fabricated in different technologies and foundries. Some of the security advantages offered by the 2.5D 3D IC include split manufacturing, where since the different dies are fabricated or designed in a different technology node and can be fabricated using a different foundry. Therefore, the foundry do not have a complete holistic picture of the circuit, and therefore it is very difficult for the untrusted foundry to reverse engineer. In addition to the split manufacturing, the 3D IC also offers new security features. That means that it offers the heterogeneous integration of CMOS and non-CMOS based technology. For example, chemical or MEM sensors can be used which are non-CMOS for the detection of Trojans or to prevent the probing attack. The second security benefit is it enhances the existing security metrics. That means that addition of a trusted control plane on top of an untrusted compute plane to monitor the behavior. That means for the use of used to detect the presence of a Trojan can be performed using this additional plane. And third one, it reduces the overhead of security application. That means that die stacking structure enable high performance processing memory encryption to reduce the memory security overhead. In addition to that, a different obfuscation plane can be fabricated without increasing the additional area of the functional plane, which still improves the security, but also not impacting the overall area of the functional die. Yeah, in addition to the security advantages, the 2.5D and 3D IC also offers security challenges. These include in form of challenges in the design phase, where the use of untrusted EDA tools and untrusted third-party IPs it can lead to the insertion of Trojans, where the Trojan extracts the secret information or alters the functionality of the IP. One more security challenges is during the fabrication phase, where untrusted fabrication facility can insert a Trojan tier without the knowledge of the designers, and these Trojan tiers can now snoop on the secret information or can alter the functionality of the IC. So the challenge also they offer security challenges during the testing phase due to complexity and high cost and time for testing the 3D IC thoroughly. The most of the testing is carried out in an offshore facility. Therefore, this results in an untrusted testing process. In addition to that, the testing process, the use of probes to test the TSVs can also damage these TSVs. Therefore, the testing process is not thorough enough, and therefore this might lead to the non-detection of a TSV-based Trojan or multi-tier-based Trojans. One more disadvantage of the 3D IC is that it has a large temperature gradient. Therefore, these are susceptible to the thermal-based side channel analysis, and also it also susceptible to the power-based side channel analysis. So in general, the security of the 3D IC can be broadly classified into two. There is a Trojan insertion and the side channel attacks. In the Trojan insertion can again be broadly classified based on the activation mechanism. So that is, they can be broadly classified as thermal and non-thermal activated Trojans. And depending on the location of this Trojan in the 3D IC, the Trojan insertion can again be subclassified as Interposer or TSC based Trojan or cross-tier located Trojans. Coming to the side channel attacks, the side channel attack can be broadly classified as thermal and power-based side channel attack. So in this part, I'll be discussing about the hardware Trojans in the 2.5D and 3D ICs. So a hardware Trojan is any malicious component that alters the functionality of the IC or causes undesired effect like a denial of service attack in the IC. So as I said earlier, the hardware Trojan in the 3D IC based on the activation mechanism can be classified as thermal activated or non-thermal activated. And depending on the location of these Trojans, can further be classified as TSV located or cross-tier based located Trojans. So we'll be discussing about the thermal based Trojan initially. So the thermal based Trojans are again subdivided based on the location. It is the Interposer based and cross-tier based Trojans. In the Interposer or TSV located Trojans, the threat model consists of an untrusted fabrication facility or an integration facility. So the one of the example of a thermal-based TSV Trojan is a switch that connects between the two TSVs, and when the temperature conditions are met, the switch is turned on, therefore resulting in a short circuit between the two TSVs. This short circuit will lead to the denial of service attack or modifies the actual functionality of the IC. Coming to the cross-tier based thermal activated Trojan, the threat model is that of an untrusted foundry. Due to the large temperature gradient, the 3D ICs have a large temperature related issues. So the NBTI is one of them. So the NBTI results in timing glitches. These timing glitches are then utilized as the Trojan activation, where when these timing glitches are present because of the NBTI, it now changes the state from a legal state to a redundant state, and therefore this redundant state now causes a denial of service. So these are the few examples of a thermally activated Trojans present in 2.5D and 3D ICs. Coming to the non-thermal based Trojans, the non-thermal based Trojans can be broadly classified on the based on the location, that is on the TSV. So these are subdivided into power TSVs and signal TSVs. And the threat model for both of them is that of an untrusted foundry. So the composition of the TSV can be changed, as well as the dimensions of these TSVs can be changed. So this leads to the changes in the parasitic resistance and capacitance. That means the per unit length resistance of the TSV or per unit length the capacitance of the TSV are altered. So in the power-based TSV, now by altering the composition or the dimension of the TSV, the VDD supply to this inverter can is now changed. Therefore, this results in 15% reduction in the peak power and 11% increase in the peak delay of this inverter. This might this causes timing issues in the later part of the signal chain. Coming to the signal-based TSVs, here the per unit resistance and per unit capacitance of the TSVs are altered. Now, for example, here when the two inverters are connected to Trojan TSV, that means that composition and the dimensions are altered. This results in 90 picosecond increase in the delay between the two signals, between the two inverters, and then 100 femtofarad change in the effective capacitance, and then further results in 2x increase in the peak power consumption of the load inverter. And this again can be used for signal integrity issues in the later half of the signal chain. Coming to the non-thermal activated cross-tier Trojans, so these are broadly classified into 4 different cases. In the case 1, the trigger is placed in one tier while the payload is located in another tier, and this consists of a Trojan is a heat generator with a thermistor-based payload. So the thermistor-based payload modifies the delay of the critical paths and leads to the timing violations. In the second case is that of a cross-tier based Trojans, where the payload is placed in the top tier and facilitates for the easy probing or measurement of the side channel analysis. The third case is that of a Trojan that is activated by trigger circuits on the multiple tier. And this is the example can be that of a NOC, where a malicious IP in one tier send NOC instruction to victim tier in a different tier, victim core in the different tier through the malicious switch. And fourth one is multi-tier based Trojans, where Trojan tier consists of a malicious IP core and switches that monitor the exchange of packets to the middle tier. This results in a snooping type of attack to determine the secret AS encryption keys. So this is the brief summary of the Trojans present in the 2.5D and 3D ICs, and further information can be found in the paper. Coming to the side channel attacks on the 2.5D and 3D circuits, the side channel attack consists of exploiting the intrinsic physical signal produced by an IC during normal operation. The side channel analysis can be broadly classified as power, timing, temperature, and DM based analysis. So in the 2.5D or the 3D IC, the research on the side channel analysis is very limited, and the models and countermeasures that was developed for the 2D IC cannot be directly applied to the 2.5D and the 3D circuits. One of the main source of the side channel signals are the thermal and power, and therefore the side channel analysis on 2.5D are broadly classified as thermal and power based side channel analysis. Coming to the thermal-based side channel analysis, this example is that of an Intel Xeon processor that has an octa-core processor. So we are monitoring the different temperature sensors are placed in different cores. We are just monitoring the temperature variations on the core 3. Therefore, as you can see that as the temperature of the core 3 changes, the temperature sensor in the different cores also detect these changes in the temperature. Therefore, that any changes in the one of the core can be monitored from the another core. See, applying the similar logic to the 3D ICs, the use of a Trojan plane can be used to snoop in on the cryptographic code that is present in the bottom tier, and using the temperature sensor can determine the activity of the AES core, and therefore leads to the Trojan that can either release a EM signal or enhances the side channel analysis, or can be used for easy probing of the circuit. A different type of approach is using the correlation thermal pattern from the power and activity. So this includes a 4-step process. In the first step, the attacker applies a broad and varied range of input patterns in a step-by-step approach to trigger different activity patterns in the circuit. In the second step consists of localization and monitoring of modules, wherein the thermal side channel signals are monitored, and based on monitoring this, the attacker builds a thermal behavior of the IC. Now, a Pearson coefficient between the power profile and the thermal profile are developed, and you're using this PCC, a correct encryption key is obtained. The further procedure of the and the results of this approach are provided in this paper here. The second attack is that on the general purpose processor using thermal tracers. The thermal tracers are obtained using either one of the 3 steps, using the thermal based sensor in form of Trojan, or external thermal sensor using depackaging or infrared imaging. So an accurate model of the IC is constructed using statistical signal pattern technique between the thermal tracers and the input-output responses. And based on this statistical pattern technique, secret key of the circuit is estimated. Coming to the power-based side channel analysis, the power-based side channel consists of a simple differential and correlated power analysis, out of which the correlated power analysis produces the most accurate results. And therefore, the further discussion on the power-based side channel only is based on the correlated power analysis. So this is an example of using the correlated power analysis on the S box of the AES key. So different scenarios of the X box switching has been performed, wherein different planes are switched on and off using the 4 scenarios, and comparing the power of these 4 scenarios without of a 2D IC, a PCC score is determined. The scenario that results in the activation of only 1 tier produces the highest PCC score. Therefore, now employing the localization and monitoring modules that we discussed previously, the secret key of the 3D IC can be obtained. The final is that on the monolithic 3D IC. The monolithic 3D IC are usually fabricated using a single foundry. Therefore, to protect the circuit against untrusted foundry, logic locking based approach is typically used. This is in form of a standard out-of-cone logic locking technique as shown in this figure here. So the correlated power attack on the locked monolithic IC consists of the following procedures. The first procedure is to use a logic cone extraction. That means logic cone of the locked netlist are extracted based on the primary outputs, and then divide and conquer based power estimation is performed, where the correlation power attacks on the are executed on each of the logic cone on an ascending order of the logic cone size. Further, the power traces are collected. The power consumption of all the logic core are extracted for the same input pattern. Now, using the correlating the estimated power with the collected power, correlation Pearson coefficient is determined, and using the PCC, the correct encryption key is obtained. The further information and the results are provided in the paper shown below. So this is the brief summary of these different side channel analysis on 2.5D and 3D ICs, and much information are provided in the paper. This is the conclusion. So the vulnerabilities of 2.5D and 3D IC in form of Trojan insertion and side channel analysis are presented. The hardware Trojans are further divided into thermal activated and non-thermal activated, and TSVs and crosshair structure used for thermal implementation, and these are very hard to detect during testing because of its difficulty and complexity in the testing procedure. And the side channel attacks on 2.5D and 2.5D and 3D IC includes power and thermal-based side channel attacks, and detailed analysis of different vulnerabilities of the 2.5D and 3D ICs are presented. The goal is to enhance the understanding of various Trojans and side channel leakage model for the unique to the 2.5D and 3D ICs. This increases this promotes a further research and development of different obfuscation procedure for the 2.5D and 3D IC, which are still in nascency at the current stage. Thank you.